this is a combustion reaction. If you were going to give me the simplest definition of a combustion reaction you could, what would it be? Oh, okay, I asked for that. That's exactly what I asked for. If you were going to look at a reaction written out in a reaction, so there was no flames involved, it's written out, how would you know something was a combustion reaction? What do you need for fire? Oxygen. A combustion reaction is a reaction where something reacts with oxygen, O2, and releases a lot of heat. That's a combustion reaction. It's a reaction with oxygen that happens very fast. This is rust. This is iron chains that are rusting. What do you know about the reaction that forms rust? What is the iron reacting with? Oxygen. It's oxidation. And so this is iron reacting with oxygen. This is a match reacting with oxygen. But what can you say about the speed at which those two reactions happen? That's really fast, and that's really slow. But they're essentially the same reaction. So why does that happen fast and that one happens slow? We talk about these as reaction rates. Rate is speed. Reaction rate is reaction speed. And so, like we just saw, some reactions happen very fast. Some happen very slowly. And so we have to figure out why. How can we predict what speed they're going to go by? Without looking at your notes, if you had to guess, what can you do to speed up a reaction? What do you think you can do to make something react faster? Heat. If you raise the temperature of something, it reacts faster. That's one thing. Imagine you're mixing two things. What do you think you can do to those to make them react faster? Stir them. If you stir them, you're going to mix them better, and so they're going to react better. And they're going to react faster. So, first one up here is temperature. Higher, in most cases, higher temperature means a faster reaction. I think stirring is not even up there, but yes, you're right. Second one is reactant concentration. So, imagine you're in lab, and you're taking two solutions that you made, and you're pouring them together, just like we did when we made the chalk. If your two solutions are very dilute, there's not much solid dissolved in there, there wasn't much calcium chloride or sodium carbonate, you don't have much reactant, and so you have very low concentration solutions. When you mix them together, it's not going to react very fast. We'll talk about why. But if you have more concentrated reactants, it's going to react faster. Just like with dissolving. We said if you increase surface area, things will dissolve faster. Because we said you need the water touching the solid that it wants to dissolve. When you have a big sugar cube, the sugar in the middle is not touching the water. So it can't dissolve. Same thing is happening here. If you are reacting, let's say, a solid with a liquid, that solid has to touch the liquid in order for it to react. So if you have a chunk of metal, the metal in the solid in the middle, metal in the middle of that chunk isn't touching the liquid on the outside. So it can't react. But if you grind that metal up in the dust and mix it, pretty much all of the metal is then touching the liquid and it can all react. So increasing surface area increases reaction rate. And then the last one, the one you probably never would have come up with, is the presence of a catalyst. If you add a catalyst to a reaction, it will happen faster. Catalysts increase the rate of reaction, and again, we'll talk about what exactly a catalyst is. So these are two reactions. Here we have the befores, and then afters. And so imagine this is vinegar, and we're going to add baking soda into it. So here we have low concentration vinegar and high concentration vinegar. We add the same amount of baking soda to both. Which one would you say reacted faster? The one on the right. When you react baking soda and vinegar, you get bubbles. So in this case, the bubbles are filling the balloon. And so this one had a high concentration of reactant. There's a lot of vinegar down here. It reacted a lot faster. This is surface area. So what we have here are sealed containers with oxygen in them. And then we have, you can't see it, there are wires coming down, hooked up to electricity. This is an iron nail. This is iron wool. You hook the electricity up to that, it glows. You hook the electricity up to the iron wool, and it goes crazy. This is oxidizing. This is reacting with the oxygen in here, but it's happening very slowly. Over here, it's again reacting with the oxygen, but it's happening very fast. Why is this one so much faster than that one? If you can imagine steel wool, there's a lot of surface area there, right? They're tiny, tiny little threads of metal. There's a lot of surface area, so almost all of the iron is exposed to the oxygen. When you put the electricity through, what the electricity is doing is causing heat. It's heating it up. It's giving it a little punch to make the reaction go. But here, the only reaction that's happening is the small amount of metal that's actually exposed to the oxygen. Over here, almost all of it is. So it's going to go really, really fast. This is catalysis. Catalysis is the process of using a catalyst to speed up a reaction. So this is a piece of liver. In the liver, there is an enzyme called catalase. Catalase breaks down hydrogen peroxide to give off a gas. Okay, so if you take liver and you put hydrogen peroxide on it, it bubbles. It's speeding up the breakdown of hydrogen peroxide. If you just take hydrogen peroxide and set it on the bench, eventually it will break down. A catalyst doesn't make anything happen that wasn't already going to happen. It's just going to make it happen a lot faster. So this reaction is a very visual reaction. Catalase is an enzyme. How many people have taken anatomy and physiology? So enzymes are catalysts. That is what they are. They are proteins that are catalysts. They make reactions happen. And so in every cell in our body, all the enzymes are catalyzing reactions. You just can't see it. This is just a reaction with a catalyst that you can actually see. So in order to explain why these things affect a reaction, we have to understand the requirements for two things to react. And so we're going to move back into that molecular level way of thinking about two molecules coming together and reacting. And we call this collision theory. We say that for two molecules or atoms to react, they have to actually collide with each other. If one's over here and one's over here, they're never going to meet and they're never going to react. They have to be moving and they have to collide with each other. And when they collide, there are certain requirements that have to be met when they collide. It's not just a matter of whether they hit. So imagine you have two molecules. Each molecule is made up of a dark atom and a white one. And let's say that this is going to be a synthesis reaction. So these two molecules are going to come together and make one. And once that happens, what it makes is that. Are you able to look at these two and see how they have to be oriented when they hit in order to make that? Yes. So I had a couple of people nodding their head. What do these need to look like when they hit? Right. When they come together, the two black ones have to hit each other. It looks like the two black ones are the glue. They are the ones that actually react with each other, hold it together. So if they hit like that, if those two just came together, that's not going to react. They're not in the correct orientation.
So it's like Velcro?
Yes. So that's a great example. And so if you have two of the soft parts of the Velcro, they hit together, it's not going to stick. If you have two of the prickly parts, they hit together, they're not going to stick. And also, not only do they have to be in the right orientation, but they have to hit hard enough. Imagine throwing a piece of clay up against the wall. You have to, if you throw it hard enough, it's going to stick. But if you throw it very softly, it's just going to hit and bounce off. Same thing happens in a reaction. Even if these two molecules hit in the correct orientation, if they just very gently bump into each other, they're not going to react. They have to hit with the correct orientation, and they have to hit each other hard. So, we talked about energy diagrams before. So we said that there are exothermic reactions and there are endothermic reactions. What's the difference between them? Right, one gives off heat and one absorbs heat. Which one's which? Exothermic reactions give off heat. So we drew energy diagrams before. And we said one of them looks like that, and one of them looks like that. Which one's which? Endo's on the left. This one is endo. This is an endothermic reaction. So this is time. And this was energy. And so we started with this much energy, and then we ended with that much energy. Over here, we started here and ended down here. Now that I've drawn these, I don't think we even drew the little humps before, did we? I think we just went like that. Anybody remember? I think we did this? Okay. Today, we're going to add the little hump. That hump is important, though. It's not correct without it. And so we're going to expand our understanding of these energy diagrams. So in order to understand the energy diagram, here's an example. So imagine I'm sitting at home. I'm on the couch, and I decide I want ice cream. Okay? But I don't have ice cream. Not only is it out of reach in the freezer, I just straight up don't have ice cream. So if I want ice cream, I'm going to have to get up off the couch, go to the store, get my ice cream, and come home. And so, in this case, having energy is a bad thing. Having energy is the opposite of having happiness. So here, I'm sitting at home on the couch, eating my ice cream. I'm very happy. I want to have as little energy as possible. When I start off, I'm here. But I have to get up off the couch, drive to the store, I get less happy when I do that. It takes energy to get up off the couch to go to the store. We call this an activation barrier. It's the energy that you have to put in to get from point A to point B. Yes, in the end, I'll be happier than I am now at the beginning sitting on the couch. But I have to decide, do I have enough energy to go to the store, to get over the hump, to get to where I want to go? That's what we're going to be doing with our model. So this is the same exact type of a graph, but with a reaction. So here we have ozone. Ozone is O3. It's going to react with NO. So here we have ozone and NO. In the end, it's going to give us O2 and NO2. But in between here and here, when those two molecules hit each other, for one split instant, we have one big molecule. Even though in the end, they're going to hit and then break apart, for that one split instant, it's one big molecule. And we call that a transition state. Because it is neither this, it is neither that, and this will never exist for more than a split second. This is not something you can reach into a beaker and pull out. And so it goes from here to here, but it has to go over a hump, just like a roller coaster. You come out of the station, you get on a little chain thing, it takes you up, but then once you're at the top, there's no turning back, and you go down. So you need to get over this activation barrier. The activation barrier is the difference in energy between here and here. The difference between where you start and the top of the peak. So that's the energy barrier. It's also called the activation energy. So energy, the little a, is activation energy. And then once you're up here, then you can go wherever the reaction wants to take you. If we add a catalyst, the reason we increase the rate of the reaction is because we lower the hill. What a catalyst essentially does is it takes the one big hill and turns it into two small hills. And so what you need to think about is if you have a reaction happening in a beaker. Remember, you have all of these molecules flying around hitting each other. Some of them are going to have enough energy when they hit to react. Some of them are not. The lower you set that bar, the more of them are going to have enough. Just like if I said, we're going to have a pizza party in class next Tuesday for anyone that has an 80% in the class. Some of you will have enough. Some of you will not. But if I set the bar at 20%, a lot more of you, I think all of you, will have enough for the pizza party. So what the catalyst ends up doing is it lowers the bar. A greater fraction of the molecules in there have enough energy to get over the hump. Does that make sense? So if you were to be asked a question of what a catalyst does, your answer would be it lowers the activation energy. That's what it does. And by doing that, you increase the rate because a lot more of them can get over the hill and down. Does that make sense? Good? So one place you probably use it with, well, I hope you use it, whether you know it or not, is in your car. There is something in your car called a catalytic converter. I'm not a mechanic, but I believe the catalytic converter is just off the engine. Right when the exhaust comes out of the engine, it goes into the catalytic converter. The catalytic converter is coated with platinum. Yes, it's platinum, it's very expensive, but it's a very, very, very thin coating. There's nothing, not worth much. And so when you do that, when you burn the gasoline in your engine, you get different combustion products. You get oxygen, and you get carbon monoxide. Carbon monoxide is bad. We don't want to be putting carbon monoxide out in the air where everybody's going to breathe it. But if oxygen comes and it sticks to the platinum in your catalytic converter, and the carbon monoxide comes and sticks next to it, they'll actually get held in place there, they'll react with each other, and then CO2 comes off. Yes, we're now learning that CO2 is not great on its own either, but at least it's not toxic to breathe. And so you're converting the toxic carbon monoxide to non-toxic CO2. Essentially what it does is it holds them in place. They would react with each other anyways, but it's a slow process. And so the platinum holds them in place and lets them react before they float away. So we're going to do an example of one of these energy diagrams. So we have a reaction. We have NO2 is going to give us NO and O2. And we're going to draw an energy diagram. It says, draw an energy diagram that shows the relative energies of the reactants, products, and transition state. And then we have to label them. Molecular representations of the reactants, products, and the gas, and what the activated complex is the transition state, what we think that splunk is going to look like. So I'm just going to draw a set of axes. If you're drawing this graph, what unit, what is on the x-axis? What is down here? Puppies?
It's a reaction. Reaction.
Time. Somebody said time. So this is as the reaction proceeds. We're going from left to right. What is on the y-axis? Energy. And it just goes up. So we have to first decide where the reactants and the products are going to be in terms of up and down. What in there tells you that? Endothermic. So it's endothermic, so that tells us where do you want me to put my reactants? Higher or lower?
Low and then up.
Let's just pick a spot. So in relation to that, where will my products be? Higher. It's endothermic, so it's going to absorb. So should it be here, or should it be up here? It actually doesn't matter. As long as it's above that. It doesn't tell us how endothermic it is. So you could put it here, you could put it up here, we'll just pick a happy medium and put it there. So if we're going to go and start from here and end there, what is the line going to look like between here and there? Is it going to look like that?
No.
Or like that?
That's straight. Right.
Is it going to look like that?
Up.
It's gotta have the hump. Even if, so in the examples we had before, we had an exothermic reaction, where it'd start here, it'd go up, and then it'd end up down here. You always have to have the hump, and the hump is the highest point in the graph. Always. That transition state is always the highest point. So you go from your reactants up to the transition state, and then you have to come down to the products. It's just a matter of how far down do you come. Do you come down to a point above here or a point below here? So this is endothermic. So we're going to start here, go up, and then only come down a little bit. And so if you're going to label the reactants. where on here would you label, where would you write is the reactants? Here, here, or here? This one, A, B, or C? A. So these are reactants. Where are the products? C. These are products. What is that? Transition state. We'll just call it TS, transition state. So it also, the question wants us to label the diagram with molecular representations of the reactants and the products. So we have NO2 is our reactant. We only have one reactant. So I'm going to go NO2. A dark N in the middle and two white oxygens over on each side. Products, we have NO. So NO would be a dark one and a light one. And we have O2. So O2 is a light one and a light one. Now we got the tricky part. What the heck does our transition state look like? So essentially we have that, and we need to get that. What is a transition state going to look like?
You're talking about reactions, right?
Yes. Give me a hint. There are coefficients here. These coefficients are going to tell you something.
Are you wanting circles and then dark circles?
Well, let's start with the numbers. So this thing, we actually have two of these. So let's draw that. And we have two of these. In what orientation can these two things hit and stick together so that when they fall back apart, they can fall apart into those three things? So Crystal's wanting it, I think, like that. So if they're stuck together like that, and we can break it apart however we want, can we break that apart into these? Yeah. If we get that, and that, and that, that works. There's actually another way. I hadn't visualized that one. That one works. How else could they hit? So you
Like, just one of the oxygens on both sides.
okay, sorry. I think, so they hit end to end. And so we get that, that, and that. They're both right. Because you can't actually grab a transition state, that means you can't measure. You can never actually figure out what it is. And so with the information we have, we don't know whether it's that one or that one. It could be both. We don't know.
So you can't draw it.
When it says, and a possible structure,
Oh.
it says, and a possible. It could not be neither of these, but either of these would be a structure. I'm pretty sure I would never ask you to do something like this on a quiz or a final. But if you can see this, you'll have a good idea in your mind of what's going on, and that'll help you then. Yeah, so this is what they had done with this one. They did the same thing. We're going to move from a reaction diagrams to reaction equilibrium. And we already used the word equilibrium one time. When did we use the word equilibrium? Remember the word? Remember the word, but you don't remember where it came from. It was vapor pressure. How did we use the term equilibrium in terms of vapor pressure? Vapor pressure was when we had a glass of water, and we had a lid on it, and then some of the water came out, some of the water molecules came up here. What does that have to do with equilibrium? What transitions, in terms of states, going between solid, liquid, gas, are happening here? We have evaporation. We're going from liquid to a gas, and what? What's the other one? We also have condensation. The gas molecules up here are coming down here. So if those two things are both happening, where does equilibrium fit in? Initially we have that, then we have that, then we have that, and it stays like that. Now where does equilibrium fit in? At the end. At the equilibrium, we said, was when the molecules were coming up at the same speed that they were going down. And so here, the molecules are coming up, and we're getting more and more gas. But once it reaches equilibrium, the gas molecules are coming down at the same frequency as the molecules that are leaving. So we call it equilibrium. Equilibrium means that the amounts stop changing. You have two things that are both happening. They're opposite processes. So evaporation is the direct opposite of condensation. They undo each other. If they're happening at the same speed, at the same rate, the amount of gas and the amount of water stop changing. The same exact thing happens in a reaction. A reaction can reach equilibrium. So here we have N2O4, it's starting here, and it's going to break down into NO2. It just simply breaks in half. So if we have a jar of N2O4, we just let it sit. Over time, it will break down into this colored NO2. And so here we see a couple of them have broken down, and then some more have broken down, and then some more have broken down. But when we write this reaction, we don't just have one arrow like normal. We have two arrows. We have an arrow going that way, and we have an arrow coming back that way. That means that not only does N2O4 break apart into NO2, but if two of these NO2s come back and hit each other, they'll make some of that also. And so in the end, you reach a point where you have some of this and some of that, and this is breaking down into that at the same exact speed that this is coming back together to form that. And so if you're measuring the amount of N2O4 in your jar and the amount of NO2 in your jar, to you, it looks like nothing is changing. On the molecular scale, these are still breaking into those, and these are still coming into these, but it's a one-for-one trade-off. And so your measurements stay the same. It looks like nothing is changing, but at the molecular level, it still is. So we can calculate what we call the equilibrium constant. The equilibrium constant tells us once you've reached equilibrium, how much reactant is there and how much product is there. It tells us, would the reaction rather be more like the reactants, so it's only going to change a little bit, or would it rather be more like the products and go almost all the way to the end and then stop? This slide probably looks very scary. It is not. This is going to be very, very simple. Okay? So, this is just a generic reaction. And so, the capital AB are two reactants. The lowercase a and b are the coefficients. Just like that, C and D are two products, and the lowercase c and d are coefficients. And then what we do is we take these and we write an equation like this. And it is always in this form. It is products over reactants. Get that little phrase stuck in your head. Products over reactants. So what you're going to do is you're going to take the C, we'll do examples, but whatever compound C is, you're going to write it, you're going to put it in brackets, and then whatever that coefficient is, you write it as an exponent. You take D, you write it there, put it in brackets, whatever that coefficient is, you put it there. Do the same thing for the reactants. A with a lowercase a, B with a lowercase b. The brackets mean molarity. And so what you're going to do is a problem will give you the molarity of these four things. You plug those numbers in, raise them to the powers, do the math, and you'll get your K. Yeah? It may still sound daunting. Once you do the first one, it's going to be really easy. So we have our reaction. The very first thing is, what is the equilibrium constant expression? When something asks the equilibrium constant expression, it's asking for KEQ. So a K is a constant. We had the KF and the KB last week. K is a constant, and then EQ stands for equilibrium. So this is the equilibrium constant. So remember that it's products over reactants. So I'm going to draw a line, and we're going to put the products up here and the reactants down here. What are the products in this reaction?
2 NH3.
In this case, there is only one product, right? Just NH3. So I'm going to put in brackets NH3, and I'm going to take the 2, the coefficient from it, and put it up there. What are my reactants? N2 and H2. So I'm going to put N2 in brackets, and I'm going to put H2 in brackets. What's the coefficient on N2? It's 1, so I'm just going to leave that off. What's the coefficient on H2? 3. So I put a 3 there. That's the first part. That is the equilibrium constant expression. We're done with the first part. Second part is, what is the value? So we need to plug in numbers for these three things. On a quiz question, they're going to be straight up given to you. They're not even going to be here is in a graph form, where you have to pull them out. On a quiz, on a final exam, they're just going to flat out tell you. So here, in our example, what is the concentration when we're at equilibrium, so we're in this graph, what is the concentration of NH3?
0.280.
0.280. 0.280, and it's squared. What is the concentration of N2? 0.060600. And that had no exponent. What is the concentration of H2? 0.180 to the third. So just do the math.
Two 24.
24? Is that what everybody else got? Anybody? Thank you. So the equilibrium constant, the value is 224. This is the only time in this course you can give me a number without a unit. There is no unit on the equilibrium value. There is no unit. So the answer is 224. Now we're going to take these numbers and we're going to say whether reaction is reactant favored or product favored. And when we say reactant favored or product favored, we're thinking about the reaction on a spectrum. We have the reactants here, and the products over here. We have this line connecting. When we hit equilibrium, we can hit equilibrium here, or here, or here, or here, or here. And so that one, we're at equilibrium, we're a lot more like we started than where we were going. Over here, we're a lot more like where we're going than where we started. So we have to figure out from this number, where on that line are we? And it's easy. This number comes from this, right? And this is products over reactants. So if you have a fraction, x over y, if x is bigger than y, is your fraction more or less than 1? It's more than 1. If the top of your fraction is bigger than your bottom, this is going to be more than 1. If x is bigger than y, x was our products. So our products are bigger than our reactants. So that is product favored. The top is bigger, that is product favored. If the equilibrium, if that value is more than 1, it is product favored. What happens if y is bigger than x? It's less than 1. This means the reactants are bigger. So it's reactant favored. This number will be less than 1. What happens if that value is 1? Exactly 1. What does that tell you? What does it tell you about this fraction? It's equal. The top and the bottom are the same. So if it is exactly 1, this number comes out to be exactly 1, it is neither product or reactant favored. It fell right in the middle. So you're going to get a K value. If the value is 1, it's neither. If it's more than 1, it's product favored. If it's less than 1, it's reactant favored. So that's exactly what this is telling us. So you got it right there on a slide. Here's another example. You have another reaction. You have NO2, well, this is the same equilibrium we were dealing with before, but it's written the other way around. In this case, the NO2 is the reactant, and the N2O4 is the product. So the first question we're asked is to write the equilibrium constant expression. So I've got KEQ. What am I going to write up on top? We've got N2O4 raised to what power? 1. The coefficient on N2O4 is 1. What's going to be on the bottom?
2
NO2. The 2 ends up there. That is the equilibrium constant expression. We're done. Part 2 says calculate the value of the equilibrium constant at 25 degrees Celsius. The 25 degrees Celsius isn't, you don't have to do anything with that. It's just changing temperature will change this. Changing temperature will change the whole equilibrium. So it's saying at 25 degrees, these are your values. So if it said at 25 degrees, these are your values, what is the equilibrium constant at 30 degrees? You can't do that. There's no way for you to predict. So we're just going to straight up use these values. So what number goes in here?
1.25.
This is N2O4, so we count 1.25. What number goes in here?
0.074.
0.075, and that's squared. If you do that math, what do you get?
222.
222? So if we get 222, is the reactant favored, product favored, or neither?
Product.
Product favored. Product favored gives you more than 1. 222 is definitely more than 1. So we did product favored. Like I just mentioned with temperature, the equilibriums are not set in stone. You can change them, and you can upset them. It's like they find their happy place, and if you poke them, all of a sudden they have to readjust to get back in their happy place. So we are going to poke them by adding and removing things. This is called Le Chatelier's principle. And so if we add a reactant or product, we can add product. Imagine we have some sitting in a jar over here, we can dump some in. We can add a product, or we can actually take something out. If we have a way to pull out a product or pull out a reactant, we can adjust the equilibrium. So imagine, let's say, you have an imaginary reaction. Okay, we don't even know what the reaction is. But that number is a 2, that one's a 4. So our equilibrium constant is 1/2. Is this product, reactant, or neither favored? This is reactant favored. So this number is the product, this one is the reactants, and they always have to equal 1/2. Imagine I have a way of reaching in, pulling out some product. I pull out half of the product. Does that divided by that now equal 1/2? No. So it is no longer in its happy place. So it is going to adjust. It's going to take some of this to make some of that in order to get back to 1/2. So we're going to talk about reactions shifting in one direction, shifting left, or shifting right. And so when you're doing this, you're going to have the reaction written out in front of you. A few ways that we can poke it and make it not happy. We can add or remove a reactant or product, like we just said. We can change the volume of the reaction container. This only works if what we're doing is a gas reaction. So if you have a reaction happening in water, and it's in a 100 milliliter beaker, and you pour it into a 500 milliliter beaker, that's not going to make a difference. Gases, remember, fill their container. And so if you put it into a container, you can change the concentration of that gas. Or you can change the temperature. If you change the temperature, you change the KEQ value. So what I really need you to get out of this is the part where we add or remove reactants and products. The other two are not so important. It's the adding and removing things that's important. If we add something, we say that the reaction shifts away from it. You add something. You now have too much of it. It was in its happy place. It had how much it wanted, and then you added more. It doesn't want more. So it's going to take that and break it down into the other side. So here is our example reaction. It's just A plus B is going to give us C and D. If we add reactant, if we add some of the A or we add some of the B, we say it's going to shift away from that. It's going to shift to the products. We say it shifts right. You add something on the left, it shifts right. If we add product, we now have too much product. So it's going to decompose and go backwards here. So we say it will shift left. If we add reactant, we have too much reactant. So we're going to make more product. If we add product, we have too much product. So somewhere it's going to go backwards to make a reactant. Doing it the other way, if we remove some reactant, all of a sudden we don't have enough. And so we say the reaction is going to shift towards what we took out. Some of this is going to have to come backwards to replace what we lost. If we pull out product, some of your reactant is going to have to react to come over here to replace what you lost. So this is a generic table saying if we add reactant, it shifts right, add product, shift left, remove reactant, shift left, remove product, shift right. So we'll have examples of it. So if you could look at the molecular level and see what's happening, this is what it would look like. Imagine we have this equilibrium. We have atoms or molecules that can magically convert between yellow and green. So when they're at equilibrium, we have 1, 2, 3, 4, 5 yellows and a whole bunch of greens. But if we have an eyedropper, we're able to go in and just suck out some of the yellows. All of a sudden, the ratio between the yellows and the greens is messed up. We now don't have nearly as many greens as the yellows as we started, but the greens stayed the same. So some of our greens are going to convert back into yellow. We removed reactant, the product shifted towards it to replace what we pulled out. So I always think of it as if you pull something out, it's going to shift towards it. You have to make more of what you got rid of. You have to replace it. If you add more in, all of a sudden you have too much of it. So you're going to shift away from it. You need to get rid of it. So we have this reaction, and we're going to do some stuff to it. We have to predict which direction the reaction is going to shift. So number one is silver ion is removed. It says, it gives us how, but that's not important. Because NaOH is not up here anywhere. And so what you need to focus on is silver ion is removed. Is silver ion a product or a reactant? Silver ion is a product. So if you remove some of that, is the reaction going to shift left or shift right?
Right.
It's going to shift right. If I pull this out, I have to replace it. And so this is going to come over here to replace what I removed. If I add silver nitrate, keeping in mind that silver nitrate will dissolve in water, is my reaction going to shift left or shift right? Is silver nitrate up there? No, it's not. So we first have to decide, is this going to affect anything? Or is this a trick question? What's going to happen when we put silver nitrate into our water?
Dissolve.
It's going to dissolve. And when it dissolves, what's going to happen? It's going to break apart into ions. So by adding this, we are adding that. So if I add silver ion, will the reaction shift left or will shift right?
Left.
It will shift left. We now have too much of this, so it's going to come over here to get rid of it. What if I add sodium iodide? Keeping in mind that sodium iodide will dissolve. Will it shift left? Will it shift right?
Right.
Which one?
Right.
What are you going to end up, what are you actually going to do when you add sodium iodide? You're removing something, you're adding something. Which
Well,
thing
you're
are
adding
you
to the
adding?
left side, so it will pull it to the right, right? Correct?
Are you adding to the left? No.
Adding product, right?
The product.
You're adding product.
Okay.
You're going to be adding the iodide. So just like adding here, except here we're adding that.
Okay.
So we're still adding a product, it's still going to shift to the left. What if I had a way, well, it says this is a solid, right? So imagine this is going on in a beaker, and that solid is sitting at the bottom of the beaker. What if I take my eyedropper, and I go in there and I suck up the solid sitting at the bottom of the beaker? Is that going to shift this reaction left or right? Why left?
As you remove or the reactant.
Reactant. So we said, I sucked up the solid. Solid is that. I'm removing this. If I remove that, I now don't have enough. So this will come back this way to replace it. And that's the end. Questions? So really, there's three main parts to that lecture. There's drawing the energy diagram. There's doing the equilibrium expression. And then there's shifting equilibrium. If you're comfortable in those, you should be fine. Remember that there's regular homework. So there's the online homework that will tell you about the quiz, and then there's the written. But don't forget those. We'll take our break, and we'll